Yeah, okay, so my name is Heimir. I work here at Mototech. I've been coding for a long time. But I'm pretty new to all this stuff, so bear with me. But I'm gonna give you a short introduction to OTP, gem server in particular, and I'm gonna do it in Erlang. So just make it more interesting for you guys. But it's easy. So all of this stuff is. So what this is actually I want to contrast the how you build software if you use something like the gem server or if you roll your own. And there are good reasons not to roll your own. Okay, that's basically my message. And I'll walk through a simple example of using the gem server, and it's applicable to a lot of things. In this case, it's a small server giving out like frequencies for a mobile phone, and really simple and easy to think about. And I'm going to talk about these different phases and different ways of, or actually, functionality that's provided by OTP, both for synchronous and asynchronous calls. I'll go through both of them, and the termination as well. But I'll start with the naive way of doing these things yourself, which is tempting, especially if you're really clever. So that is something to think about. But the main purpose of OTP is actually to help people build systems with these properties. It came about back in the early 90s. 1990s, not 1890s, and we're actually yeah, really, it's old, right? And when Ericsson actually had this failed C++ project that just crashed and burned, and at the same time they were more or less alienating this team there with this functional ideas and stuff. So they decided to give them a chance, and they then all of a sudden had like 60 people building something in Erlang that was brand new, and they realized that it wouldn't make much sense to have each and every developer trying to invent all these patterns in 60 different ways. So that's how OTP came about. OTP stands for actually Open Telephony Platform, but nobody uses that anymore. It was part of the politics back in the 90s to call everything open. That's where the open comes from, and of course it was a platform, and it was actually intended for telephony in the beginning. But of course, as we know, this is way more generic, and we would probably be way better off on the web if we had learned something from these guys earlier on, rather than building these idiotic web systems for a couple of decades. So, but these guys actually knew what they were doing, and these guys were actually real engineers, and they came from that culture as opposed to the web. So, and OTP actually is written in Erlang, and it is basically I would say like best practices kind of codified. It's more than a library. Libraries are some modules that you just call and they do something and they return something. But this is more like pattern and best practices that are codified in OTP. And they use, the solid system design principles is actually about how to deal with concurrency and highly distributed systems that can also fail and deal with failure as well. And so it is pretty impressive. What they do is, for the most part in OTP, is actually they call it behaviors, and what you use actually, you use this behavior in your code. as opposed to like a library call. And they have the generic server, the gen server, which is actually by far the most used, I guess. But they also have pretty valuable, other behaviors like the finite state machines. If you need to build state machines, at all, not to speak of like distributed and highly concurrent, it's not easy. And but they actually have this behavior that you can actually then use. And event handlers and things, for like logging and high traffic event streams. And then of course supervisors for for keeping this highly available. That's a category by itself. And then OTP also has applications, or actually methods to package applications to actually deploy them and do stuff. And I haven't seen, so I was looking at the Elixir exposure of OTP, and I could not find that they have actually interface yet for the finite state machines, for example.
They did. It was deprecated and pulled out.
Yeah, right. So it isn't there.
Right.
Yeah. Right. And so that is something. That's another reason to actually look at this in Erlang if you need it. But of course, I mean, it's a very short path between Elixir and Erlang, so you can actually do stuff. You can call directly into Erlang if you want to. So that's a good news. Okay. So this is an overview of what's there. I'm only gonna scratch the surface of the first topic here. I got 20 minutes. I could use 20 days, I guess, at least. So that's what I'm going to talk about. And so this is my beautiful drawing. I got 2 graphics, and this is one of them. This is the more complicated one. So bear with me. And so this is a depiction of a server. You start at the top. And the first thing you do, you initialize it. Usually you might, want to restore some state or do something to actually make the server, in where you want it. And then you basically, spend all your time in the loop in the middle. And you receive calls and you do something and constantly, until somebody sends you a special message. Which might be just a call, but we call it stop. And then we go from the evaluate loop down to terminate. And terminate is actually the opposite of initialize, where actually we can take the state and save it away, persist it or do whatever it is. And then when we are initialized again, we can find it and then restore ourselves. So this is high, this is true for almost. I mean, it's a very universal pattern of building a server, and this is what the gen server actually implements, with a little bit more, but I mean this is in practice what it does, and has things to preserve state between calls and do stuff, and I'll talk about that a little bit later, because this is then like a symbolic code of what this does. I mean, and this is kind of Erlang. So the in line 1, I mean, that's a method to actually start the server, and it might have some arguments. In Erlang, variables have start with the capital letter. Everything else, I mean, lowercase things are actually atoms. So just bear that in mind. And what the start would do would actually, spawn the server, actually start the server somehow as a separate process, and then call the init function. And you can see in line 2, I mean, there's a reference to the init function.
And the period means. And
the period is simply the end of the statement, end of the function. So it's commas and periods, just like sentences in English. So it's pretty easy, right?
And semicolons.
And semicolons, of course.
It's got all of them.
Yeah, exactly. So it's just like plain English. Sort of.
Sort of. Good one, Joe.
Exactly. Okay, so and I mean this is just like the main things. The init or initialization would somehow use the arguments to establish the state of the server. I mean, the arguments might be a name of a file. I mean, it might be anything, of course. But then the init function ends by calling the loop and pass the state into the loop. And that's where we then spend all the time. And then the loop is just basically receiving some handle and a message. And then it calculates a new state based on the message coming in and the current state. We call that message, call that function handle. It's a reference to the real code that I'll show you later. And then it actually calls itself with a new state, ready to actually receive the next message, or actually the next call. And then, of course, if it gets a stop, it will call the terminate and pass the state down to terminate, remember? Because then terminate can do anything with it, do a cleanup and save it away and do stuff, okay? So this is actually the next step. I mean, this is codifying the picture in the previous slide. Any questions on this?
The equivalent of handle and stop in here, those are atoms, right?
Yes, those are atoms. I mean, all the lowercase, green things are actually atoms. Yeah, so I mean, yeah, just ask me if there are any and this is actually just like a Zoido code, if you like. So okay. So let's build a server with real code that really runs, and I call it a naive server because it's very simple. And if you haven't built a server before, if you never dealt with any kind of concurrency or anything, this is what you would probably do, which is a bad thing. But it's what we all do. I mean, we have to make our own mistakes usually to actually learn from them, right? So in order to make this more reusable, let's split this into two modules. The generic module, I have that in server.erl, that's an Erlang code for the server. And then another module, which is actually only for callbacks, because I want to have the server module totally generic and be able to do anything. And including this really important function that I'm going to implement, which is allocating mobile frequencies, okay? And that's why I'm actually calling this thing allocate. And that's if you think about it, that's just more or less like callback functions, or that you provide for the server to be able to run your specific thing. And the idea being that you can then reuse that server, for any kind of server, but you would also just provide different callback modules depending on what you're doing. Okay, so this is then some code that actually implements the server, and it's a module called server, and it has these four functions: start with 2 arguments, stop with 1, call with 2 arguments, init with 2, and then actually you can see the actual code, and this runs fine. The start method does nothing but register the name that is passed, and in my case I pass the name of allocate, which is my module actually, and I reuse it. It's actually used for both things. So I register a server called allocate, and that's the first name in the register, or first argument, and then I spawn a server. And that's ourselves using the init function. So the server argument there in line 6 is actually a reference to the module, and init is reference to the function in that module, which is the init function in line 8. And then I pass these 2 arguments to the init function, and I actually reuse the name coming in as a module name for the init function. And moving forward, once the init function is now running after this spawn, it's running now in that server process. I actually create the state, my state object, and this is in the server, remember, by calling my module, which is the allocate module, which you haven't seen yet. So it's a forward reference, so I hope you don't panic. And calling an init function there with my arguments. And then I just call the loop. So this is more or less the same flow as you saw before in the simplistic version, but now it's actually a real code. So then I call the loop and pass down the module name and the state that I calculated in line 9. And that's basically where we spend our time. And you can see the receive clause has two patterns. It can either receive a request or a stop. So this again is more or less the same as you saw before. And this is a little bit more. I mean, there has to be some code around this so it really works, but this is more or less the same thing. It actually gets, it takes the request and then there's a callback. So I'm calling back into the allocate module in this case, call a method called handle and give it the message. So I'm going back and forth. So the server is doing basically just handing these things, back to my module when I do a call. And then I do something, and then I call the reply function to actually reply back to the client, and then call myself again recursively. So I just loop there forever until I get a stop. And when I get a stop, on the other hand, I actually I calculate the reply, and then send call the terminate function in the module, and then do a reply back to the module. Okay, is this clear? And then the rest of the server is this. I mean, it's the start function, and it actually sends a message. So the bang is actually a message, sending the stop, and it's paid, to the process. The name process, and then receiving the reply. And then you can see the call is actually the external call that actually is then ending in the loop all the time. We're just sending a message to ourselves with the request and waiting for the reply. Any questions on this?
So that bang is kind of like the Elixir send?
Send, yes. It's the same function as send, except the bang is not in front. Mm-hmm. It's between. Okay. So you're sending, the stop self in line 24, for example. Mm-hmm. Sending, this tuple, the atom stop, and my self is my PID to the process called name. Which is server. I'm actually sending it to myself. So it's a way to actually stop. But the client is calling stop on the server, but the server is actually then sending itself, hey, stop. And it's a bit convoluted, but it makes it totally generic. So all these things. I mean, state is never defined in this. The state is whatever I want it to be, and that's where the client comes in. Okay, so this is like 30 lines of code that is needed for like a basic server, and that can do anything, almost. Okay, not very well, but I mean it can. Okay. So then it's a callback module, and that's even smaller because it's only 19 lines. And this one is called allocate. It has these functions. And it has this start function, and the start function actually calls the server module, the start method, passes the atom allocate, which is actually the name of itself, actually of the module in this case, and then an empty argument list, because I don't need to pass anything. And then actually the init function was then called by the server as a result of calling start on the server. There's a callback to init on the client, and that's what happens there is actually init actually returns this tuple, which is the array coming from get frequencies and an empty array or empty list. So get frequencies is actually specifying all the mobile frequencies available from 10 to 15, all 6 of them. And then the frequencies thing in this is basically just 2 arrays. The first, I mean, this tuple is actually, my state is basically the tuple of 2 lists. One of the frequencies available and the other one of the frequencies in use. So I can have like the allocate function is to actually give me back a frequency or an error, and then the deallocate function actually returns that frequency back to the pool, and then actually the other things are just like housekeeping things for the stop. That's just calling the stop. That in turn will actually call terminate in our code. So this is pure callback, and this way I can implement whatever I want to as a server by using the same server module all the time, right? The second half of this is actually less interesting. This is actually the actual logic, which is not important at this point, but basically what it does on allocate, the first step in line 26 is actually I'm calling allocate, and my state is an empty array. So I'm all out of frequencies, and then the allocated array or allocated list and the PID, which I don't use. That's why it's underscore. Okay. Then in that case, I will return what I got, the frequencies together with the tuple error and no frequency. So that's basically returning an error back. In other cases, where I actually do have a frequency, I will actually in line 28. That's just a list with frec as the first element, followed by the free, which might be empty, obviously. So that's just a list thing, and the allocated and the PID. And what I do is actually I return the free part, which is actually the thing behind the frequency, the first number, and then I actually add that frequency to the allocated frequencies, and then I return an OK and the frequency. And deallocate does the opposite. There's actually a nice bug in the deallocate, because if you deallocate the same frequency twice, it is actually just duplicated into the list. But yeah, we can fix that bug later, okay? But the code is simple enough. The handles up there in 21 and 23 are again the callbacks by the server when I do a call, and those simply translate the atom allocate into calling the allocate function, and the atom deallocate calling the other function. Yep.
So on 26, you have the underscore in front of PID.
Yeah.
Does that mean
it's ignored? Yeah.
Even by the VM?
Yeah.
Okay.
It's ignored. Yeah. Any other question? Yeah. So underscore variables in Erlang are just ignored. Okay. So and this works. Okay. I'm not going to do it because we're short of time. But just trust me, it works. This is actually straight from the textbook anyway. So I did some typos in the beginning, but I fixed them, and it's working. So it's real code. So this looks all fine. On paper. There's nothing wrong with this. The logic is working, and I get when the list is empty. I get the correct error back and everything. But there are several problems with this. And this is maybe the most loaded slide in this presentation. So the first one is actually we might get a reply from somebody else. Okay, that's a big problem, right? So if our client is actually getting a message from somebody that's not the server it called, right? That's a nasty problem. Okay, so there's a fix to that. A pretty easy fix to many of these things. There's a make reference library call that simply makes like a random string, and you pass that to the server, and then you expect it back on all replies. And then you just match on it and say, okay, I ignore everything else. So that's cool, okay? But that's minor thing. But all the crash scenarios are really nasty. Usually are in distributed systems. And like in this case, if the server crashes just before we actually do a send, we will be hanging in the receive part, waiting for the reply coming back from the server forever. I mean, there's no way out. Sorry, dead client. So that's not good. But then we can fix that by doing something else. We can actually there's a monitor thing. Instead of actually spawn link, which we could do, but then we would actually cross the client too. So we could actually do a monitor. But then we have to do a demonitor. And there's another race condition around that, which actually, there's a small window where we could actually, the server could actually crash immediately after it sent us a reply, before we can actually demonitor it, and it's going to be a mess. And these are actually just more more scenarios of the same sort. And this, of course, is something that the Erlang guys ran into back in the early 90s, and that's why they actually came up with this Gen server. And deadlock is actually one of them, of course. I mean, if you have two servers, A and B, and they call, both do a synchronous call to each other, they just wait there and hang, and the system is hung. So it's not a good situation to be in. This is just a list of some of the issues that are actually inherent in this simple code that I presented, and that's why I call it naive, because it is, and it's just optimistic, actually too optimistic to be put into production, and hoping that it works, because it will fail. One of these conditions will definitely come up in production one day. So that is actually their motivation. That's why they came up with OTP and began to solve these problems properly. And they basically did this. I mean, that's why I came up with this. I'm leading into this pattern. But what they did was they created this Gen server, which is actually a behavior module written in Erlang. And then if you use this, you only have to write the callbacks. Okay, the server is there. So saves you half the typing at least. This is a great thing, right? And so this is actually the thing that you need to do, and it's actually implemented with something called behavior. So on line 2. So I create a module. This module is called frequency, and line 2 actually says I want to use the behavior Gen server. That's it. And then actually all my things are actually available, and the server is there in my code and everything. And then I simply export my regular variables, and this API is a bit richer than the naive one. But not much. I mean, it's pretty compact and easy to understand. Then this is my code for the callback module, and the start in line 8 is very similar to the line that you saw in my naive server, but it's calling the Gen server. And it's using a method called startLink, and this, and you know, when you read about these things, they say never use spawn or spawn link or send in your own code, because you know, unless you want trouble, and that is actually there's a good reason for it. It's because you open up this kind of worms I was talking about, you know, all the the failure scenarios and all those things. So they actually have this as a method. So as the client simply calls that method, and things are taken care of by the behavior, you know, correctly. In the gen server, we actually have like the first argument is the name of the module. It's referring to the module. My module name is actually frequency. It's running on the local server. It can be running, you know, on a cluster. The name of the package here again is repeated. The name of the module, and then there are two extra arguments that I don't use. The third one, I mean, this one is the arguments passed into init. So that might be my state restoration if needed. And then there's the fifth one, which is options. And I can set various options for the gen server behavior, like, you know, different timeout and stuff like that. By default, all calls to gen server timeout in 5 seconds, actually 5,000 milliseconds actually. But you can actually change that behavior. But that by itself prevents most deadlocks, because they will simply time out trying to talk to each other, and you can't do something about the situation without crashing everything and burning. Okay, and in this case,
you've got 20 seconds.
I can speak fast, you know. In this case, in line 12, you can see actually my state is called frequencies. And it does more or less what the other code did. Actually, it calls the get frequencies, which is the same method as before, and an empty array. And then the init function returns OK, and the state variable back to the server. So remember, this is my code, and so now the server actually has, after init, it has my state variable. So this is pretty clean and simple, right? Then the allocate function is something that I was using in my code, and it simply does call to the gen server, and this is a synchronous call, meaning I block my process while I send it to the server, and the server actually is treating these calls you know, in sequence as well, so it doesn't screw up the state or anything. And this is one type of call. So the call itself is straightforward and simple, and then my callback handler is here, and it's it's almost the same code as I had in the naive implementation, because I mean that's all I need, and except I mean like in line 19, I actually calculate the new frequencies. And I get the process ID to actually send back to the reply. And so new frequencies is actually, you know, what is left of frequencies once I've allocated one. And the new loop state. So the state variable is actually in the loop of the server constantly, just going around. And I calculate it in my code, of course, and the server just passes it along. Okay, any questions on this?
There's one important point, is that when the code inside the allocate function is running, that's running in the process that's calling it.
Yes.
When you get inside the handle call, that's the process of the gen server, a different process.
Yes, exactly. Yeah. Yep. And
Wait,
this.
sorry.
The allocate is a public function.
This is a public. Yeah, this is a client function. Actually, this is running
Right,
in the client process. This is actually running in the server process.
Right, so one process might call allocate, but a separate process would receive it in the handle.
No, the server is running the handle call.
Right.
Yeah, this code is running in the context of the server.
Right.
And so you have everything, you know, defined in the server available there too. So this is interesting. Another class of calls is actually asynchronous calls. fire and forget stuff. In this case, I mean, I'm using it for the deallocate because I don't have to wait. I just, want to return that frequency. And the same thing for the stop. And instead of using call in line 23, it's called cast. It's like multicast or broadcast or whatever it is. It's simply something you throw, and you don't care about anything coming back. So it's not a call. And again, it's very simple. The functions themselves, and you can see the handle cast is very simple too, except there is no reply. On line 30, what I return is a no reply, because it's not supposed to be sent as a reply back to the client. But the state, the calculated state, of course, is returned into the loop of the server. So that is important. So that's how this basically is running. And then on the other hand, in line 31 is the handler for the stop. So now I want to stop the server. That's asynchronous too. But if the first argument in the handle, any of the handle functions, handle call or handle cast or whatever it is, if that's the atom stop, we will go to the terminate thing. So that is actually a pretty easy way of stopping these things, and it's totally generic. And again, I turn the second argument in line 31 is the loop data. I don't call it frequencies. I mean, it's just a loop data. I don't care what it is. I just pass it along. I'm not using it as the frequencies. I mean, it is, but I don't have to know that. I just handle it. And the loop data is then passed down to the terminate function. There is one more. So we have handle. We have handle call for the synchronous thing. We have handle cast for the asynchronous things, and we have handle info for everything else. So if somebody sends a message to this server, if I don't do anything, it will just simply crash, because it doesn't know what to do with this message. If I write the handle info method, I can simply say, okay, I get this message, and I get the state variable. So in this case, I just print out whatever was sent to me in a friendly way, with a new line and everything. You can see the tilde n. It's a new line. Cool stuff. And then I just give a no reply back to the server. Say, okay, I'm ignoring this. This is something I don't know what is. But if you don't do it, I mean, you might actually, and of course in regular systems, I mean, you would not actually want to.
It won't crash the system if you're not handling it. It'll just get stuck in the mailbox, right?
No, you would actually crash the server.
Yeah.
Yep. I mean, that's how it's designed. Yeah. And it should, actually. So I mean, if you're getting something that you're not expecting, I mean, hey, I mean, don't ignore it. And absolutely not keep it in a mailbox and have the mailbox just fill up. And that's
you have just a regular process. I mean, not a gen server, just a regular process to receive. If it doesn't pattern match, it'll just sit in the box.
Yes. Second.
Yeah,
but gen server
crash
will.
that process.
No, but the gen server will.
Yes, the gen server actually behaves differently. So it is intentionally crashing on those things, because it should not be the case. And there's a small list of things that that you should read up about on that behavior, depending on what you want. I mean, if you want, like, undefined codes just to be ignored, you just write code to do that. But otherwise, it crashes because it doesn't pattern match, and it just, performs a suicide, which is actually healthy, in these systems, right? Okay, and so in this case, this is just a random thing. The terminate is actually then the last part. If any of these handle functions returns a stop, we will get a call back to our terminate function, and we will get the loop data. In this case, I do nothing, so both of them have underscores, so I don't care. I can get the reason, and the reason in practice can be really important. I mean, what's going on? Why am I crashing, or why am I stopping? Is it just a normal stop? Okay, then save my state. Is everything just on fire? Hey, I mean, I better not. Maybe save state. That's wrong. I mean, there are things here that are really, really hard to think about, in practice. Okay, and then of course, like I said before, I mean, we can save the state because we get it in the happy path, and then we can actually use that back in the init function to actually restore the server the way we want it. Okay. Oops. Yeah. So I'm not gonna run this either because it's trivial, and I'm all out of time. Even though I speak fast, it's not enough. So I knew it would take some time. But so I mean, these are actually my conclusions. I mean, don't write it yourself. I mean, that's basically the only. If you had one message to take away from this, don't write the server yourself. Use the Gen server. It's easy to use and it's bulletproof. It's been tested for decades, and in many cases running for years. I mean, in live systems in production. You need to read the documentation at least once to actually figure out these. I mean, who needs to read documentation? But there are options if you read it. Okay, if you read it, you actually find options to deal with like these unexpected cases. So this was only scratching the surface of the Gen server. Then there are, you know, like all these other beautiful things in OTP. So that's my talk. I actually have one more slide. So.
Can you talk about Gen server in the context of a cluster of servers?
No, I'm too stupid.
Do you want to?
No, I'm too stupid. No, I haven't read about it, so I haven't used it, so I would not want to go there. There will be follow-up talks, okay?
Because also on handle info, I thought this was also used, you know, for cross-process communication as well.
Yeah, it is.
Have you heard of the little Elixir OTP guidebook?
Yeah.
Yeah, that goes into nodes and using Gen server to
Right,
manage
right.
state across
Yeah,
nodes.
yeah.
Right.
I just want to make a comment on that. There's a distributed Erlang, which is a different, I mean, it is still Erlang, but it's used for distributed communication between distributed classes. So we have some stuff in there for that.
Yeah, I mean, Erlang is distributed by design
Yeah.
from the beginning, so there's no thing, you know, distributed Erlang is not a thing. Erlang is distributed. So you can use it across multiple nodes on multiple servers, you know, just as it is. So, but it's a different talk, okay? But Erlang is actually his name was Erlang because he was a Dane. He actually was admitted to the University of Copenhagen when he was 14 and studied mathematics. So he was a mathematician and a statistician and an engineer as well. He worked for Kotas, which is actually Københavns telefonaktieselskab, which actually is the Copenhagen telephones company, and is now actually has changed a couple of times, has changed names a couple of times, but it was actually it was started about 1880. It's TDC has now like 8.5 million subscribers, so it's by far the biggest phone company in Denmark. He actually invented traffic engineering and queuing theory, and that's what he did. And it's very interesting to read some of his papers from 1907, you know, where he's actually, you know, laying out the mathematics and the foundation for all traffic engineering. For example, I mean, in 1909, he proved that these like telephone traffic and actually a lot of other traffic, like any traffic where people actually come in by random, is actually a Poisson distribution. What?
Queuing traffic, like
queuing traffic, yes.
Going to a
Yes.
checkout counter.
Exactly. Yeah, checkout counters, you know, barber shops. I mean, you know, whatever, and the web, by the way, and the phone systems in particular. And that's where he actually figured it out. And actually, I mean, utilization of phone lines was what he was working on, figuring out how many switchboard operators he needed for a particular trunk in the system, and how many lines between trunks, and that's where it came from. And now actually there is this unit of traffic is Erlang. I mean, if the line or actually the system is fully utilized, it's one Erlang. That's what it is. So it's a unitless measure. And the funny thing is actually I was working for TTC for a while in year 2000. So he was actually dead then for like 50 years, but no, actually 70 years. So yeah, that's it. That's Erlang. Thank you.